So it's my pleasure to welcome Michele Lanza to Microsoft. So Michele is Associate Professor at the University of Lugano in Switzerland, where he leads the REVEAL group, which is short for Reverse Engineering, Visualization, and Software Evolution and Analysis. Almost. Michele has served on many PCs. He was PC chair of many conferences, like, for example, the MSR conference, which is actually not the Microsoft Research Conference, but the Conference on Mining Software Repositories. And next year, he is PC co-chair of ICSM 2010 in Romania. So, please, Michele.
Thanks. So, thanks for having me here. Let's start with a little prologue about myself. So, my name, as Tom already said, is Michele Lanza. I'm Italian. So I was born and grew up in Italy and moved around a quarter of a century ago to Switzerland, where I did a PhD at the end at the University of Bern. And then in 2004, I moved to Lugano. So that's really as beautiful as that picture, but it's also a boring town. Noteworthy things about me are maybe this thing. So I wrote a book together with Radu Marinescu on metrics. I'm actually fairly proud of the book. I also call it 2.5 years of blood and sweat. And another thing which is noteworthy about me is that I'm actually a small talker, so all the things we do are actually written in small talk. So, as Tom said, in Lugano I lead a research group whose research interests revolve around 3 main domains. So I have currently 1 postdoc and 6 PhD students. So I will not really mention 2 of the 7 topics here because these PhD students just started this year. And I will focus mostly on immersive soft visualization for this talk. But feel free to talk to me about any other of those things there. So just to give you a brief introduction to this. So one of the things we do is called fine-grained software evolution. That work was done by Romain Rob. In the meantime, he has become a PhD, so a doctor. So the things we did there was basically to observe that versioning systems, as mainstream versioning systems, are basically not sufficient when it comes to modeling software evolution, because basically they are snapshot based, so they are based on when somebody wants to commit to the repository, and because of this, if somebody doesn't commit for hours or days, it means that you basically lose a lot of information. So what we did in this case was to develop a system called spyware, which we presented at ICSI last year, which basically tracks every single change that happens in the system as it happens. And then we reify those changes as first-class objects, and we can do several things with those changes. So, for example, we used it to enhance a code completion engine by an order of magnitude in terms of precision. Or, for example, one of the things we also did was basically that you can take a set of changes, and of course these changes are hard-coded in a sense on the system on which they have been applied, and you can abstract them away and basically create custom refactorings on the fly. So this is fairly interesting work. Another work is done by Mircea Lungu. He's about to get his PhD next month. Here basically we started in reverse architecting software systems, and at a certain point in time we thought that we actually have to go 1 level higher, which we call software ecosystems, which is basically the set of software systems as they live together in a certain organization. So, for example, SourceForge can be considered a software ecosystem. So we have developed for this a web-based tool platform which allows us to analyze hundreds of software systems as they live together. And like this, you can, for example, track developers, how they move from one project to the other, what kind of relationships projects have with each other, how active people are during which time, and so on. Another axis of work is done by Marco D'Ambros. This is on bug analysis and prediction, where we again developed a tool platform, and we have developed a couple of different approaches to, first of all, analyze software bugs, in the sense that software bugs have a lifetime. They are born and then they live or co-live together with the system for a certain time until they are closed down or still remain in the system. This is another work done by Lile Hattori. This is basically a continuation of the work by Romain Rob, where we basically took the spyware-based approach to another language because spyware was built in Smalltalk. In this case, we work on Java, which has a lot of implications because Java is a file-based language, and because of that, it's actually not so easy to extract changes as they happen. So basically, we developed a tool plugin for Eclipse, which can capture the changes as they happen. And then we do several things with them. And this is also in the context of collaborative software engineering. So basically, the point here is to not only track changes as they happen, but as they happen in a collaborative context. So when several people work in parallel on the same system, and then we developed mechanism, for example, of notifying people if something happens at the same time that somebody is changing the system. In this talk, I will mostly focus on the work of Richard Vettel, which is about immersive software visualization. So I named the talk Seeing Software. So first of all, I should explain what seeing is all about. Now, seeing, of course, is understanding. And we are visual beings. So 70% of all brain inputs come through the eyes. In reality, we actually see with our brain. We don't really see with the eyes. And there's 3 types of memory that process visual information. There's iconic memory, which is like a register, short-term memory, which is a working memory, and long-term memory. Now, I won't go into long-term memory because this is more psychology than anything else. Now, about iconic and short-term memory. So iconic memory is basically a buffer that retains information for less than 1 second before it passes it on to the short-term memory. And perception, in this case, is limited to a very limited set of attributes. Perception is very fast, it's automatic, it's subconscious, and because of this, it's called also pre-attentive perception. Then there's also short-term memory, where the information is processed in the form of chunks. And perception, again, is temporary, that's a couple of seconds, and in case the information is not rehearsed by the brain, it usually goes lost. And it also has limited capacity. So that's 3 to 9 chunks, depending on your brain, basically. And if you add another chunk to short-term memory, basically one of the chunks will fall out. This, for example, explains why charts are more expressive than tables, because if you look at the chart, basically the brain chunks the whole information that is presented to it, and then can suck in the information better. While if you look at the table, basically you have to read the table, and this just takes longer. Now, I will focus on pre-attentive processing attributes. And just to give you a couple of examples, now these are pre-attentive attributes of form, which are very relevant for software visualization. So what I will show now is a couple of very simple diagrams. And what will happen is that there's always one element which is different from the others. And your brain will process that, the fact that one of the elements is different, before you can actually react. So for example, there's orientation, there's line length, there's line width, there's size, there's shape, there's curvature, there's added marks, there's enclosure. These are just now the attributes of form. There's also attributes of color, of motion, and so on. Now, if you apply this to software, let's just start with something which is very simple, and probably this is the most simple visualization you can have of software. So you have an entity in a software system, like a class, and you just display it as a box. Of course, systems are composed of more than one class, so maybe you have a second class, and if they have a relation together, you can draw an edge between them. That's just a very simple application of pre-attentive processing attributes. If you now apply this on a real system, you obtain something like this. Now, this is a very small software system that's classes and inheritance relationships, and you can already start now to interpret what you see. So you see, for example, there's 2 inheritance hierarchies in the system. There's a couple of classes that are standalone. One of the hierarchies is actually larger. And if you look at the larger hierarchy, you'll see that it has sub-hierarchies as well. For example, this one or this one. Now, what you can do with this, of course, is fairly limited. Now, if you just use a very simple idea called polymetric views, you just enrich now this simple visualization with a couple of software metrics. So imagine that, for example, for the width of a node, you use the number of attributes. For the height of a node, you use the number of methods, and for the color, from white to black, you use the lines of code. So this makes you go from here to here. So that's the same system now enriched with metrics. And now what you can start doing is interpreting what you actually see. So of course you may think that, well, let's focus first of all on the big stuff or on the dark stuff. But that's not really the point. So of course one of the things that strikes the eye is an element like that, which means it's a class, it has a lot of methods. It's very dark, which means it has a lot of lines of code. Now if you compare it with this class here, that class actually has even more methods, but it's lighter, which means that the black guy here has longer methods in average. Or other things that I see is putting things in a context. For example, if you look at this sub-hierarchy here, now classes in a hierarchy, usually they are related to each other. Otherwise, they wouldn't be siblings in a hierarchy. So for example, here you see that this class is way larger than its siblings. And it means that there is something noteworthy about this class compared to its context. Now, if you scale this up, you obtain something like this. So this, for example, is Argo UML. That's a 120, 130 KLOC system written in Java. It's a UML modeling tool. And here now you can start to interpret what you see. So one of the things that really strikes the eye, of course, is this thing here. That class, of course, that's an older version of Argo UML. That class was called model facade. So it's a facade pattern. And it has an incredible number of methods, an incredible number of attributes, and is around 5,000 lines of code long, which is abnormal compared to the rest of the system. So I'm not saying that it's abnormal to have such a big class, but it's abnormal to have it so big in its context, because the rest of the system is more or less well balanced. Actually, what happens with this class here, so this is a God class, is that developers of Argo UML basically pushed any piece of functionality that they were not really sure where they should put it, they pushed it inside that class. So the class over time grows like a cancer in the system. Actually, what then happened later on is that they refactored the class, and I will show a couple of visualizations about this as well. So other things you can see, for example, are particular hierarchies where there's one superclass and then dozens of subclasses. And if you look, the subclasses, for example, are all very similar in terms of raw number of methods. And if you go and have a look there, you will see that a lot of code is duplicated. Now, of course, this is just a picture. So one of the things that you need to do if you have such pictures is to interact with them. So like 10 years ago, I wrote a tool called CodeCrawler, which was fairly famous. In the meantime, we have rewritten it as an Eclipse plugin called X-Ray. And this basically is integrated inside Eclipse. So if you click on a class here, you basically get to the code. If you click on the code, you get to the visualization and so on. And you can navigate back and forth. So this is the first part on seeing. The second part is software, because the talk is called Seeing Software. So if you look at the definition of software, according to Wikipedia, software is the soft parts of a computer system, and it's the intangible objects inside the computer. Now, if you ask any developer what software really is, usually the answer will be that software is basically composed of text. Now, if source code is text, then what follows is that programming is writing. That's also what General Weinberg said in the Psychology of Computer Programming, is that programming is some kind of writing, which I actually disagree with, because 30 years ago it was like that. In the meantime, we're in the 21st century. So in a way, things should change, but they still didn't change. And what you get is, for example, things like that. This is the world's smallest chess program. It's actually a working program. It's 133 lines of code of C, and it's actually a working chess program. But I think this just goes a little bit too far. Now, this is all about people being used to certain things. So, of course, you learn programming by opening up a text editor, and then you write text inside, you compile the source code, and you obtain a running program. Now, in the remainder of this talk, I would like to basically fight a little bit this notion. So let's talk about seeing software. Now, the first thing I have to do is, of course, define soft visualization. So that's the definition according to John Stasko, which in my opinion is way too long. So let's make it a little bit shorter. So soft visualization is the use of computer graphics to facilitate the understanding of software. So soft visualizations, for sure, is not this. Okay, so this comes actually from the obfuscated C contest. So this is a runnable program written in C. It's just formatted in a funny way. Now, visualization is depicting things. So one of the sentences that you often encounter is this, that a picture is worth 1,000 words. I actually also think that this is wrong, because it's not about talking randomly about things. Visualization, most of all, is about stories. If you have a visualization and you can talk about it in a meaningful way, then it means that visualization is useful. So maybe the for me, greatest example of a visualization that is actually a story is this thing here. What is depicted here is the campaign of Napoleon to Russia. So you see here on the right side, the army leaves. The thing is wide because there were lots of people. At the beginning, there were 422,000 soldiers. So as they march towards east, and as you see, it was very cold during that year, people start dying. Okay? So there's also some people that branch off at a certain moment, and as they go on, they die more and more. Of course, because they didn't have the right shoes and so on. And as you see, for example, when they encounter a river, the thing also reduces itself suddenly in size, because crossing a river back then was really hard. So in the end, when they arrive finally at Moscow, there were only 100,000 soldiers left, which of course was not enough to conquer Moscow. And what happened is that they basically retreated and tried to get back to France. And this was then a real catastrophe. And as they go back, in the end, 10,000 people got back. So 410,000 people died. Now, that's, for me, a beautiful example of a visualization. Another thing which often shows up when you talk about visualization is UML. So this. Now, the question is this soft visualization? Well, in my opinion, UML basically took the thing with the 1,000 words too literally. Because to interpret such a diagram, you need to talk way too much. And the point of UML is not really that. The point of UML is to describe design and is to discuss design. And in a way, it succeeded at doing that. It's really a universal language. If you give this diagram to a programmer in Brazil or in China or in Europe, all of them will be able to interpret this. Software visualization has one problem, which I actually call Ball's dilemma, and that is that software is intangible because it has no physical shape or size. So how can you possibly visualize something that has no equivalent in reality? Now, I think that you can basically solve Ball's dilemma by using metaphors. So a couple of years ago, I read a very nice book by Richard Gabriel called Patterns of Software, and in that book he talks about this concept of habitability, which is the feeling that you get when you are inside a software system, looking at the code, and you feel cozy in a way, because you're confident about the code and it's easy to change it. Now, if you take this a little bit further, and that's what we did, basically we try to visualize software systems as cities. How do you do that? Well, first of all, you have to have a domain mapping. So we map classes on buildings in a city. We map packages to districts. And then the whole system is one city. We enrich this again with metrics. So for example, in this case, number of methods represents the height of a building, and number of attributes represents the base size. And if you apply this on a larger system, you get something like this. Now, this is again ArgUML. That's another version, a later version. Actually, this is a transitional version. So the large class from before is here. And what they did as a first transition was to create a new class called NSUML model facade. And what they started doing was basically copy over source code from one class to the other. And that's the twin now. Now, you may wonder, okay, so what do we do with this? Now, there's a couple of applications that we used. The first one is large-scale program comprehension. The second one is evolution analysis. And the third one is displaying software defects or software problems. Now, just about large-scale program comprehension, I don't really have the time to go and reverse engineer a full system. One of the things I will do now is just show you some kind of hall of fame of software systems. So again, this is ArgUML. Now, this is a really recent version. This is from like 2 months ago. So you'll see the system in the meantime has grown as well. So it's 167K. It nearly has 3,000 classes. And what you can do now with this is look at patterns inside the system. So one of the patterns is the thing we call parking lots. So this or this. Parking lots are basically classes which have very few methods. That's why they are not really high. They are not tall, but they have a lot of attributes. So this one here or this one here. So basically these are data classes. So they just define hundreds of attributes, and then that's what the class is used for. Or you have these office buildings. So these are classes which are large, both in terms of number of methods and in terms of number of attributes. So these are potential God classes in the system. Then you also have these antenna-like buildings there. These antennas are classes which have a lot of methods, but basically no attributes. So actually in this case, since this is Java, these are interfaces in the system. So they just define hundreds of methods, and then they are reused by the other classes. So let's just look at a couple of systems, and you will see that across systems there's patterns that you can identify. So this, for example, is Apache Cocoon, 4,000 classes, a little bit larger than ArgoUML. Here, for example, you see that compared to ArgoUML, the functionality of the system is better distributed among the classes. There's no real large outlier. Of course, these classes here are large, but it's not a real outlier in that sense. Another one, even a larger system, nearly 6,000 classes, is FrostWire. This is again a Java system. So here you see that the patterns are completely different. And you also see other patterns. For example, these things here. So these are little houses where people live in. Okay. So it's very small classes. So for example, plugins or packages containing plugins often look like that. Next one, even larger, is this one here, Jitterbit. That one is over 10,000 classes. And you see that nearly the whole system is well balanced in terms of functionality distribution, but there's a couple of outliers here, like this here or those over there. What this also allows you to spot are fundamental problems, something like this. Now this is called OpenSwing. It has actually a lot of classes, but there's just one class here which is humongously big. Yeah, actually if you rotate it, you see some of the other classes, but you see there's some major problem in here. Or the inverse problem, this is Apache B-Cell. You have a humongously big data container, and then another one which is also very, very large. And it's not that these systems have few classes. This one, for example, has 550 classes. This one can even be worse than this. For example, this is HSQLDB. That's a 160,000 lines of code system, and they just define some very large data containers. Scaling up a little bit, this goes already towards the 500,000 lines of code. This is Views. That's a famous BitTorrent client. Here we see that's, for example, for me, the definition of a nice system or a beautiful system. If you actually cross the language boundary, you also see that systems written in different languages actually look different. So this, for example, is in C++. And C++ systems always have this strange shape that there's a couple of humongous buildings and then a scattered smaller buildings. Or, for example, this one here is June. That's an OpenGL application. It's written in Smalltalk. And again, you see that the pattern of the whole system is different. What we also can do is multi-language visualization of systems. So this is now 10 systems written in Java, Smalltalk, and C++. And regarding scalability, we also did a couple of tests. So now this is nearly 1.3 million lines of code. And of course, this is a tool. So it means that it's not just a picture. You can fly inside, rotate it, do things with it, colorize things, and so on. If there is time at the end, I will also give a little demo on this. Now that's the first application. Another thing we did with this is to apply this on software evolution. And the goal here is to understand software evolution. So the first thing you can do is create film strips. So here, for example, you see 10 snapshots of ArgoUML from 2002 to 2007. And you see here the rise and fall of model facade. In 2002, model facade was not around. Then in 2003, it showed up. and then it grew very, very fast into 2004, and then it was refactored. So they created an interface out of that class, which then was called facade, and then there was also an SUML model facade, and there was also an implementation of this. And in the end, this thing slowly shrinks. So what they did basically was a major overhaul of the system, and I think they were pretty successful at doing that. So they got rid basically of a cancer in the system. One of the things you can also do is create movies. So this, for example, is an animation of JMOL over the course of 8 years. Every frame that you see represents a bi-monthly snapshot. So what you see here, this is an application to model molecules in 3D. At the beginning, the system is fairly small. They are doing little work on it. Then at a certain moment, they start extending the system, add more and more classes. And at one moment, they do a major overhaul of the architecture. They copy over, basically. They create new packages and start copying functionality over to the rest of the system. And what happens towards the end is that the system grows in an abnormal way. So here, I think things got slightly out of hand here. Okay. And again, you see something like that, it's just humongously large. Okay. One of the things you can also do is to use color to represent the age of software artifacts in a system. That's what we call the age map. So this is now again Argo UML. And what you see here is, again, the whole system. The lighter the things are in the system, the newer they are. So the more recent they have been changed. So for example, you see here that there is a class called Java Recognizer and Java Token Types. So it's an office building with the corresponding parking lot. And they also have the C++ equivalent of that called CPP parser and STDC token types. And you see that the C++ part of Argo UML came later. Okay. We actually, yes?
So when you do these evolutionary diagrams, how do you keep the sort of location stable, right? I mean, you want the same building to appear in the same spot as the software evolves.
We basically do not model classes, but we model classes as class histories. So basically we look at the whole evolution of the system, and then we assign to each class history its position in the system by taking into account its maximum size during the evolution. And then that one is like the place it uses. Yes.
The layout for the first.
Exactly. This also means that with time, there's empty spaces in the system because they were abandoned. We actually can push this also one level down regarding granularity. So in this case, we represent classes just as the base of such buildings, and each cube here now is a method in the system. And we again combine this with the age of methods in this case, and you see again different patterns coming up. For example, this whole package here is brand new compared to the rest of the system. There's also classes which look like this. So there's a bunch of methods which is really old, and then they add more methods in a more recent version, and so on. So these, for example, are classes which are all being changed constantly. While something like this is just very new, and then you have buildings like that which have been the same all the time. So they were created once, and then they remained like this. I can also show a little animation of this. So here we start with, in 2000, the system is called JHotDraw. Then in 2001, of course, the things get a little bit older. Then September 2001, March 2002, August 2002, and you see the patterns. When a method is removed from the building, basically we create an empty space. So you really see the buildings get fragmented. And I think it's also a nice way of depicting decay in a sense. Then in 2003, the system gets older, but they still work on certain things. And then suddenly, there's a whole package which shows up at once. This package here is actually called test. So they added all tests at once. So we thought like, well, it's a time span of basically half a year. So did it really take them half a year to add the tests? In reality, no, it took them like 2 days. So if you look at the history, in 2 days they added all this. So then when we talked to the developer about this, he said that basically these are all generated test cases, and they are empty. So these are all methods which are empty, basically. So that's why it was easy to create them all at once. And it looks good, of course, if the system is tested well. And then we go to January 2004. Another application is how to display design problems in a system. So here we use the metaphor of disease maps, where you use a gray color for the things which are not affected by problems, and other colors for the things which are affected. So this, for example, is JDK 1.5. All the blue buildings here are God classes. That's the same view from above. You can also push this down to method level. So this is now JMOL, and all the methods which are yellow are affected by feature envy, which in this case is around a quarter of the system. I think it's a nice way to display this. It really looks like it's pervading the system. This is just a subpart of ArguML, the model package. And in this case, we display methods which suffer from shotgun surgery. OK, with respect to tool support, we built all this inside a tool called CodeCity. It's a multi-platform tool because it's written in Smalltalk, so it's also released for Windows. And in the meantime, we have quite a number of downloads. But I guess I can give a very short demo on this. Let me see. OK. So this is basically the configuration panel of CodeCity. And what you can do now is you can take one system, and you can say, OK, I would like to have a look at the city. In this case, now it's arguml.023.4. Now it's building the whole visual model, and in the end, it renders the figures. And that's what you obtain. So now what you can do in here is, first of all, you can get closer, you can move around, you can rotate the whole thing, and you can also click on things, get information about them, like metrics and so on. If, in case you have the source code just in parallel to the model, you can also directly jump to the source code and just look at the source code itself. So things you can do here now is, first of all, navigate around. You can colorize things. So you can basically tag them with colors, and then the color are added to the model of the system, so that if you open it later on, you can get back to those colors. One of the things you can also do is display design problems. For example, let's have a look at the God classes in the system. And here you see, for example, this one here is a God class. What I would like to know now is with whom this God class is related. I can display now relationships, for example, inheritance, invocation, and access. I can use a nice yellow color for this. I can accept this. Let's see. This may take some time because it's a God class, so it's heavily connected. And of course, there's also Murphy around, right? Which is always around. Let's just try again. So this is, let's just try with that. OK. Let's try also this. OK, so now this works. So here, for example, now you see all inheritance, incoming and outgoing relationships of this class. I can add now the invocations to it. And you see it's quite connected inside the system. One of the things I can also do is I can, for example, display just a more fine-grained view, like this. OK, now I do this on this system called iText. I guess it's some kind of text editor written in Java. Rendering the figures takes slightly longer because there's just more things to be rendered. The system is not optimized at all, by the way. And that's what you obtain. And now again, you can get closer, and you can inspect things and so on. So in this case, for example, I can now colorize, for example, brain methods or methods affected by feature envy, and so on. And you see the system does have quite a number of problems. One of the things I can also do is look at the evolution of things. So in this case, we have 8 versions of hot draw. And I can look now at the evolving city. This will now take a little bit time because it needs to create 8 models, visual models of Jaya hot draw, which is not a small system. Well, maybe I should not do that on the fine-grained one because this may take even longer. So let's just load the usual coarse-grained one. Okay. And let's try that. Let's see. Okay. So now you obtain a little player here, which makes you go back and forth in time. So now you can just go back in time and see how the system changes over time. So you see, this now was the test package, which just disappeared because I'm traveling back in time. Okay, I guess that's good enough as a demo. Let me quickly come to the conclusion of this with a couple of reflections. The first one is that software visualization, if you think about it, is a good means to make the intangible tangible. I think if you use the right metaphors, and most of all, if you make the whole thing interactive, because I don't think that you can generate a magical picture of the system, but you need to generate pictures which tell you things, and then they need to be interactive, so you can basically talk with the pictures as well. Then this can really bring a lot of benefits. It's actually not so difficult after all. So visualization is based on a very few simple attributes that mostly concern the way that our brain works. It's still in its infancy. So although there has been software visualization research for the last 20, 30 years, I think that only in the 21st century computer systems have become powerful enough to display things as the ones I have shown you. And most of all, I think it's an exciting research area. So where do we go from here? So one of the things that we are currently doing is how to display relationships. So you've seen before during the demo a little appetizer on this, but there's different ways to display relationships. One that we are currently looking at is that the relationships actually create the layout of the system. So if things are well connected, then they should be central and so on. This actually leads to a number of computationally problematic problems. So if you have a system with hundreds of thousands of relationships, which is normal, and then all of those should basically dictate the layout of the city, then you need very powerful computers. So this is one of the things we've done so far, this with bundled edges. And another thing that I am mostly interested in is to obtain hyper-realistic things. So of course the cities I've shown you were fairly simple, and in the meantime we've gone to higher quality graphics. So one of the things I would like to do in the future is to have the notion of augmented reality, because right now the interface, as I've shown you in CodeSit, is actually still pretty clumsy. Because if you click on things, then the information is displayed somehow on the side, and then you already have a disconnect. Well, it would be better if you would display it superimposed on top of the 3D reality that you see here. But this is coming. And this basically ends my talk. Thank you very much. Yes?
Can you take the city metaphor further and sort of use it for displaying other attributes like the relations, as you said? So, when you, for example, roads, you're not taking advantage of roads.
Yeah. The roads would be actually the relationships that would dictate the relationship. But it's...
Yeah, I know it's harder.
Yes.
But are there any other things you could sort of use from in this metaphor that you haven't explored yet?
No, I think that metaphors are just metaphors. They can only go a certain way. So I know the work of one guy called Thomas Panas. He actually took this a little bit further by having trees inside the city and people walking around and cars driving by, but in reality, I don't think this makes much sense, because in a software system, there are no trees. Say again.
You could do paint, for for example, the entire city could be white or black.
Yeah.
And depending on how much code coverage you have on particular pieces of code.
Oh, yes.
A particular piece of code is covered 80% of the time, only 80% of the building is painted.
Yeah.
The remaining is left over.
This is things we've already done, or for example, one of the other things we've done is use color to denote who's working and where. So activity of programmers, and then animate this through time. And this actually is very telling. But the problem is that I don't really talk about it here because it's hard to get things like that published. I also have to say that last year, for example, I was at the developer conference and I showed a preliminary version of this work, and the developers were enthusiastic. They were like, wow, this is great. But then you go to a scientific conference and people laugh at you. That's just the way it is.
What about studies on the relative value of something like this compared to something much more mundane, like statistical reports and query languages?
So that's actually something that we've been doing the last half year. So we started to basically read all the papers which were on empirical studies with human subjects, because you need human subjects for something like that. And in the meantime, we are arriving more or less to a conclusion on how to perform actually such a study. And one of the things which I found funky was that I've been told for the past many years, like, oh, you should just look at the empirical work on this, on how to evaluate visualizations. There's lots of work, but in reality, if you go and look, there's basically no real work. So one of the things that I've learned in the meantime is that if you compare something like this, then you have to compare it to something. And the question is, what is the baseline? So naively, one could think, well, the baseline, for example, is the IDE. So you give, for example, one software system to somebody and just have a couple of tasks to perform, and half of the people have this, and half of the people just have Eclipse, for example. Now, in reality, this doesn't really work. So one of the things I've learned in the meantime is that the thing you have to do is that the tool is actually the delta. So the two groups get exactly the same things. So all of them get the same amount of information, get also Eclipse and so on, and then one group gets on top of all of that the system. And they can freely choose whether they want to use it or not. And then you can measure if they can answer or perform tasks faster and better than the others. And that's the only thing that you can really do. But we are slowly coming to this. Yes?
I'm struck by the number of times when you would point either with your hands or on in your slides at some particular thing and you put a text label. Or you'd say, this was a big test directory. And the reason you know that is because of words. I mean, there's the names of things are very important to programmers. And it feels really missing from these visualizations.
Yeah, absolutely.
And just being able to point at something and see off in a side panel or a tooltip or something turns it into a game of concentration. Yeah. So any thoughts about how you would integrate words with this?
So one experiment we've done is actually to use textures on the buildings and also on the packages and so on, and that the textures actually display the name of things. But I also had to learn there that you can do it the naive way, and it's just create a texture and put it on the building. The problem then is if you rotate the building, what happens with the texture? So I've seen that in the information visualization community, there's a lot of people that actually are doing things like that. For example, if you have a 3D map of a real city, and the roads, you see the names of the roads, then as you move around, actually the names also move around. So something like that. I think the solution in this, for such a problem, is really the notion of augmented reality. That if I am looking at something around my field of vision, I get additional information on top of that. And if you think about it, for example, there have been people doing research with eye tracking devices. It actually shouldn't be that difficult. Because of course one thing is to point with the mouse. The other thing is just to look around. So you look, you rotate your head, and then the eye tracking mechanism actually knows where you're looking at. And then you just display augmented reality information.
Another thing that I wondered about the 2D plan of the city, the kind of the top-down God's eye view. Is there any sense to what's next to what, or the spatial layout, or is it just kind of happenstance?
That's an excellent question. So the layout algorithm we're using right now is a simple rectangle packing algorithm. So it tries to pack as many rectangles as possible in a surface. And this actually ignores the relationships. Because, for example, if you have 50 classes in one package, and one of those classes is connected to all the others, then logically this class should be in the middle of the district, and then all the others around it. Or, for example, if a class is mostly talking... Oh, okay.
On a couple of bases, when Mauro Carabini and I looked at people drawing code on the whiteboard, they didn't put the highly connected stuff in the middle. They would... We'll talk about this later today when we meet, but basically they use a vertical axis for the layer cake, the traditional kind of, top is the UI, the bottom is the database. And then they stripe functionality to line up across those things vertically. I've got stuff that we can look at. The other comment about put the connected stuff in the middle, that's kind of the traditional force-directed layout thing. And my friends who do graph layout for a living are helping on the schedule of some of these folks, I'm not sure. But what they found is that this is not how people do graph layouts. What you end up with is a big rat's nest in the middle, and this halo of outliers. And what makes more sense, according to them, is to put the highly connected things out in the corners, and that way that'll kind of get the gravitational attractors. So you don't put, in other words, you don't put the headquarters for Boeing, Starbucks, Microsoft, and Costco in the same, you don't put them next to each other. You spread them out so that you don't get kind of everybody trying to live at the same level.
Well, but to a certain extent, the position is for sure indicated also by to which package they belong. So I doubt that Boeing and Microsoft are in the same part of the city because they just need more space. Yeah. The other thing in this context.
But if you were looking purely at connectivity,
no, that's a really nice suggestion. Another thing I would like to do is actually that you can place your buildings where you want. So it gives you an initial layout, but then I can modify it because I think this class should just move over there because it's like the UI part, and then I can move it slightly out. And then the system should remember that. But currently this is not possible. I mean, we could implement it fairly easily, of course. But again, how do you publish on something like that? Yes?
So from your earlier comment when you were talking about the ability to visualize where there might be a tremendous amount of development effort, like where are people working at any given time in the city?
Yeah.
I'm wondering about a visualization of dependency. If part of your shipper release is dependent upon many groups finishing together and a reflection of the dependency as they move towards a release date or a ship date, is there a way to show dependency or any kind of threat or risk in the groups and their dependencies on each other over time?
Wow. That's a tough one.
Sorry.
I guess one of the things I always wanted to do, but we never got to it, is, of course, if you have people working on a certain class, then you can colorize that class according to the color of those people. But one of the things you could also do is that the people are not mapped on the buildings themselves, but around the buildings, kind of in free space. And I guess with something like that, you could do something. That you would see the efforts of people as they move around in the city, something like that.
Think about from the standpoint of, let's say, you're a manager who's very concerned about your ability to get these dependent groups to complete together for any test cycle that you're going to go through, or ultimately a release cycle, and that you want to see as soon as possible that a reliance or a dependency is going to gate your ability to get to that ship date. And if you can see it 60 days in advance, would you move resources? Like, you can start to make management decisions. And because you show this idea of going back in time, I don't know if you can forecast or go ahead in time, but you can certainly see at any given time the state of the dependencies and start to forecast or predict or have a sense of the risk forward.
Absolutely. The problem I have in this case is that I never had a scenario like that.
Okay.
So it's
a real one.
If you give me the data, then I can think of solutions.
I think this issue of using roads and sort of traffic as sort of the number of dependencies and things like that might help you, because you might see that some street evolves into a freeway and then it gets bigger and bigger over time, and so you can sort of project that, oh, we're adding more and more dependencies along the same path, basically, right? And you can sort of maybe project ahead in that scenario and say, oh, there's going to be a bottleneck here or something. I don't know, it's just...
Or something's on fire or about to be on fire. No.
It's the towering inferno visualization.
Have you thought about displaying dynamic information about executions, say?
Yeah, we've done that. So what you do basically is, I don't have a picture right now, but I can dig it up later. So basically one of the things we do there is basically switch off the light and everything goes dark, so it's like the night. And then we switch on the light in the buildings which are active at a certain moment during the trace. So you see basically how the activity goes from one part of the system to the other. And then you can also use the edges on top of that. It's actually funky. Nice question.
So let's thank Michele.
Okay, thanks.